In this video, I'm going to play around with triangles and algebra, and I'm going to derive what we know as the 45-45-90 rule for triangles. Before we do, let's just get into maybe some notation and vocabulary that we should all know. Like a right triangle, I'm using the symbol for right and the symbol for triangle. And a right triangle is just a triangle where one of the angles measures 90 degrees. And this triangle here, triangle XYZ, is a right triangle. And I've labeled the vertices of the triangle with capital letters. So this is capital X, capital Y, and capital Z. And then their corresponding side length, which is the side length opposite the angle, are the same letters but in lowercase. So I have the hypotenuse here, which is just the longest side, as lowercase z, and I have x and y as the two sides of the triangle. Off to the side, I just say if triangle XYZ is a right triangle, then there's something we know about that right triangle, and that is the Pythagorean theorem. It applies to every right triangle. So it's safe to say that the side length squared plus the side length squared, the other one, is equal to the longest side length squared. That's the Pythagorean theorem. It applies to all right triangles. I have been using the word hypotenuse. Now in this example, it's the z, but that's not always the case. So I put it kind of in parentheses. If I had labeled this triangle differently, maybe x could have been labeled as the hypotenuse. So then z squared plus y squared would have been equal to x squared. So the hypotenuse is the longest side in the right triangle, and it is opposite the angle that measures 90 degrees. A right angle is an angle that measures 90 degrees. All right, I'm just going to play around with a triangle and the Pythagorean theorem. And typically in the classroom setting, I don't tell my students what's about to happen. I just play around and then bam, we've got this cool new relationship. But I'm going to go ahead and give you a hint or tell you what's going on. I'm going to derive the 45-45-90 rule. All right. So I'm just going to play around. I'm going to play around with maybe a special right triangle, one in such a way that the two side lengths are equal to each other. You may be familiar with this notation where if you put a dash on one side length and then a same dash on the other side length, and that represents that those two side lengths are the same. When I first label this triangle though, I'm going to label it like I did before, triangle X, Y, Z. Triangle XYZ is a right triangle. The Pythagorean theorem applies. But because these two side lengths are the same, we call this triangle an isosceles triangle. Isosceles triangles have two equal or congruent angles and two congruent side lengths. So you may also remember this notation, just a little curve there and a curve there, meaning these two angles will measure the same, or they are congruent. All right. So if I have a right triangle that looks like this, well, for sure, the Pythagorean theorem will apply. So I'm going to say the Pythagorean theorem says the side length squared plus the other side length squared will equal the hypotenuse squared. But with this triangle, we know that x equals y. This symbol here with the three dots may look familiar to you. If it was one dot and then two dots down below, we call that therefore. We read this one because. So I'm just saying x is equal to y because this triangle is isosceles. And if they're equal, then I can do some substitution. If x is equal to y, then I can call y x. So I'm just going to rewrite the Pythagorean theorem. But if y is equal to x, then I'm going to call it that. All right. Well, now I have some like terms. I can combine these two. 1x squared plus 1x squared, I have 2x squared. Interesting, just playing around. I think I'll solve this relationship for x. So I'm going to divide both sides by 2. So x is equal to z squared, x squared is equal to z squared over 2. And then if I want to solve for x, I can square root both sides of the equation. So x is equal to the square root of z squared over 2. And if you're taking the square root of a quotient like this, you can do them independently. So I'm going to say x is equal to, in the numerator, simply z, and in the denominator, the square root of 2. Now in this class, we typically want to rationalize the denominator. So if I were to do that, it may also look something like this. Z times the square root of 2 all over 2. But let's look at this relationship and let's put in English what is going on here. We said if we had a situation where x and y were the same, then x is equal to z divided by the square root of 2. So this is a relationship that's always true for 45-45 right triangles. The side lengths are equal to the hypotenuse divided by the square root of 2. So I'm going to take these variables and rewrite them in English, because this alone is not quite strong enough to say that's a rule, because x and z are very dependent on this picture. But like I said earlier, you may not have x's and z's. You may have a, b, and c. So I'm going to put this in a more formal writing. I'm going to say the side lengths of an isosceles right triangle will equal the hypotenuse divided by the square root of 2. Always and forever. So, for example, let's say we have this triangle and we happen to know that it's isosceles and right, and we know that the hypotenuse is 10 and x is one of the side lengths of that isosceles right triangle. I'm going to put little curves here, little angle symbols here to represent that those two angles are indeed congruent. So we have a 45-45 90 right triangle. And I want to find x. Well, the side lengths, so these two side lengths, will be equal to the hypotenuse divided by the square root of 2. So I can simply say x is equal to the hypotenuse divided by the square root of 2. If I wanted to rationalize, I could say this is 10 times the square root of 2 over 2, which would simplify to 5 square roots of 2. Maybe a little bit nicer. And I got that value just using the 45-45 rule. I'll do one more little example and try to trip you up a little bit. Let's say we have this triangle. I'm asked to find x. Right triangle, x is there. We know this value is 10, and we know that this triangle is a right isosceles triangle. I want to find x. Well, notice what I have written above me, the 45-45-90 rule, does not mention variables, because if I tried to use this formula that said x is equal to z divided by the square root of 2, this is not that same x. This x are the sides. It's the sides of the isosceles right triangle. So in this game, 10, the side is equal to the hypotenuse divided by the square root of 2. So 10 is equal to the hypotenuse, which is x in this example, over the square root of 2. That's the 45-45 rule. And I can use this relationship to solve for x. I'm simply going to multiply both sides of the equation by the square root of 2. All right. 45-45-90 rule. I hope that made some sense. I'll see you in the next video.